In this video, we will study the distribution of 10 distinct balls into 3 distinct boxes, and a box can be empty, and this is a word mapping problem. So let us define the rules of distribution. Rule number 1, 10 balls are numbered from 1 to 10. So numbering from 1 to 10 means that these balls are distinct balls and placed in 3 boxes. Rule number 2, a box can be empty. Rule number 3, the balls are placed into the boxes in order. So we can see here the order 1, 2, 3, and the order in box C is 4, 5, 6. And the question is, what is the number of all possible order distribution of these balls into the 3 boxes? So to do that, we need to map these balls and these barriers into a sequence of letters. So we map ball number 1 into A, ball number 2 into B, ball number 3 into C, and this barrier here we map it as delta, and this barrier here between box A and box B also we map it as delta. We continue mapping these balls until ball number 10. Now these boxes and balls now as a sequence are mapped into this unique sequence here. So let us assume that all balls are in box A. So this is a situation. This is box A and all balls are in it. We map these balls as alphabetical sequence from A until L, and we have 2 barriers here. So this situation can be mapped into this sequence. So this sequence represents a situation in which all balls are in box A. Let us assume that all balls are in box B. So here is box B and all balls in it. We are going to map these ordered balls into this alphabetical sequence. And we have here the barrier between box A and box B is mapped into delta, and the barrier between box B and C is mapped also into delta. So now we have this sequence which represents the situation in which all balls are in box B. So let us study the case in which all balls are in box C. So all balls in box C, we map them as alphabetical sequence from A to L, and we map these barriers as delta. Now we can write these symbols concisely beside each other, and we have a sequence which represent the situation in which box A and B are empty and box C contains all the balls. And this is a sequence delta delta A B C D until L. So what is the number of all possible order distribution of these balls into the 3 boxes? So let us assume that we have this situation here in which box A has 2 ordered balls, box B has 5 ordered balls, and box C has 3 ordered balls. We map these first 2 balls here as A, B, and then we have a barrier here, so we place delta, and then we have these 5 balls, we map them as C, D, E, F, G, and then we have a barrier, so we map it as delta, and then we have 3 balls here, so we map them as H, K, L. We have to remember that the order of boxes A, B, and C will always remain the same, so we are not going to change the location of these boxes, so they are going to always remain in the order of A, B, and C. Now the number of all possible distribution is not more than the number of permutation of this sequence, because this sequence reflects the order of these balls into the 3 boxes. So how many symbol or how many objects do we have? We have 12, and we have 2 identical objects in it. So we have to permute this sequence to know the number of all possible order distribution, and that is permutation of 12 objects taken 12 at a time with 2 identical objects, and this is equal to 12 factorial divided by 2 factorial, which is the number of identical objects we have, and this is equal to 239,500,800 possible distribution. Let us answer the question, how many order distribution we have if we have no balls in box A. So box A has no balls, and box B and C may have the balls. So let us map these balls into box A and B, and let us place the barriers in between them. And now we have to pay attention that box A should never have any balls, so which means that delta must be fixed in this position. And the reason why, if delta is placed after A, for example, then we have 1 ball in box A, and this is contrary to the question we are asking. So out of these 12 objects, we have 1 object in fixed position, while the rest can be permuted. So we have 11 objects, and they need to be permuted. So the first one can be chosen in 11 ways, the second one can be chosen in 10 ways, and the third one in 9, and so on. So this product represents 11 factorial, and that's equal to 39,916,800. And this is the number of possible order distribution in case box A is empty. Let's ask the question, how many order distribution we have if we have 1 ball in box A. So box A should always have 1 ball, and box B and C may have any number of ordered balls. So let us map the balls first in each box, and we have the sequence. We highlighted the balls in box A with the green color, because it should always have only 1 ball, and we are going to place these barriers delta here and here to separate these balls and to create correct mapping for this situation. But we have to remember that box A must have only 1 ball, which means that this delta here must be fixed in position, because if delta moves ahead, then we have both A and B in box A, and that is contrary to our question, 1 ball only in box A. So in how many ways we can choose a ball in box A? We have 10 balls, so we can choose that in 10 ways. And in how many ways we can distribute the rest of the balls in box B and C? So number of ways is the number of permutation of the sequence here. So we have to permute this sequence in order to know that. So this sequence has how many objects? It has 10 objects. So B can be chosen in 10 ways, C can be chosen in 9, and D can be chosen in 8, and so on. So that means we have 10 factorial ways to permute this sequence, and we have 10 ways to choose a ball in box A. So now we have 2 sets. The first set contains 10 elements, and the second set contains 10 factorial elements. So how many possible ordered sequence we can get from these two sets together. In order to do that, we have to remember the multiplication principle. The multiplication principle states the following: if set U has U object and set V has V object, then the product U times V represents the occurrences of both event UV in the order of U first and V second. So here we have set U with 10 element and set V with 10 factorial element. So to know the number of ordered sequences which belongs to U first and V second, we have to multiply these elements together in the order of U first and V second, and we get 36,288,000 possible distribution for our case. Let's answer the question: how many ordered distribution we have if we have two balls in box A? So now we have two balls only on box A, no more and no less, and we are going to map these balls, and we will highlight the two balls in box A, and we will place the barriers between these balls to reflect the exact mapping of the order we have. Now we have to remember that delta here should be fixed in position, because if delta moves here, then we have 3 balls in box A, and if it moves backward, then we may have 1 ball or no balls in box A, and this is contrary to our question. Only 2 balls in box A. So let us permute this sequence in order to know the number of ways we can choose 2 balls in box A. So A can be chosen out of 10 balls, so A can be chosen in 10 ways, and B can be chosen in 9 ways. As for the sequence here, we have to permute it in order to know all possible distribution between box B and box C. So we permute the sequence only, and we have 9 objects in this distribution. So C can be chosen in 9 ways, D can be chosen in 8 ways, and the rest will follow. So how many possible permutation for this sequence we have? We have 9 factorial. And for the sequence we have 10 times 9 ways to choose 2 balls in box A. So now, in order to know the number of all possible order of these balls into the 3 boxes, we have to apply the multiplication principles. So set U has 90 elements, 10 times 9, and set V has 9 factorial elements. So in order to know the number of elements which can be formed from these 2 sets together, where the first elements belong to U and the second elements belong to V, we have to multiply them in the order of UV, and we get 32,659,200 possible distribution for the case of 2 balls in box A. Let us answer the question: how many ordered distribution we have if we have 3 balls in box A? So we started with no ball in box A, 1 ball in box A, 2, and now 3 balls in box A. So let's assume that we have only 3 balls in box A. We will map these balls, and we will put the barriers between these letters. So we have 3 balls in box A, and we highlighted them in green light, and delta here must be fixed in position. So A, B, and C can be permuted in how many ways? 10 times 9 times 8. And for this sequence, we have to permute this sequence to know the number of possible distribution between box B and C. So how many elements we have here? We have 8 objects. So D can be chosen in 8 ways and E can be chosen in 7, and so on. So we have 8 factorial possible distribution for the rest of the balls between box B and box C. And this is the number of possible distribution in box A. Again, we use the multiplication principle. So we multiply these elements which belong to U and with the element which belong to V, and we get 29,030,400 possible distribution for the case of 3 balls in box A. So we will keep asking the question, how many ordered distribution if we have 4 balls in box A, 5 balls in box A until 10, and we will summarize these results here. So this is the ordered distribution, and this is the case if we have 0 ball in box A. And this case here, as we have seen before, if we have 1 ball in box A, 2 balls in box A, 3 balls, 4 until we have 10 balls in box A. Now let us make sure that our work is correct, and that is by adding all these distribution together. So let's do that. We add them and we get our global distribution, which we computed before, and this is not more than the number of all possible ordered distribution of these 10 balls into the 3 boxes as we expected exactly. We can also write these numbers using the language of permutation without replacement. So let's see. So we have permutation of 10 elements taken 0 at a time, which is 1, and we have permutation of 10 elements taken 1 at a time, and we keep doing that until we arrive at permutation of 10 elements without replacement taken 10 at a time. And this way we can write our previous result using permutation without replacement, and of course if we add them together we get again the global distribution we found before. Thank you for watching and have a good day.